In this video, we will talk about stack buffer overflow vulnerabilities. Before we talk about the vulnerability, let's first talk about how stack works. Suppose that we have a function showing the left. Function bar calls function full. And in full, there are two variables, integer x and y, and it outputs the sum of x and y. So the way that functions cause the other function works is that at the beginning, say we're in the bar, and there is a stack pointer, RBP and RSP, laying out in the stack and pointing to some locations in the stack. Then when function full is called from bar, it will first save the RIP address into the stack. And here the saved RIP address points to the instruction, the after full. And we also call it return address. So after RIP is saved in the stack, then going to function full. When function full is executing, the first instruction is push RBP, which pushes the value of RBP into the stack. And the next is move the value of RSP to RBP. The value of RBP will be equal to RSP, both of which point to the saved RBP. The third is sub RSP from hex 50. And in this case, RSP, which points to the bottom of the stack, will move below, and then a new stack frame is formed for function full. The base address is at RBP, and then the bottom address is at RSP. Above the base address are the saved RBP as well as the saved RIP, which is the return address that points to the next instruction after calling full in bar. When function full is finished, it's going to call leave and return. For instruction leave, it's equivalent to move RSP RBP and pop RBP. So first, the value of RSP will be equal to the value of RBP. And then for pop RBP, RSP will be added by 4, and RBP will turn back to be the original value that's saved on the stack. Finally, when a return instruction is executed, the saved RIP will be popped up from the stack and moved to RIP, which points to the next instruction of full. In this case, the stack frame is back to that of function bar, and RIP will point to printf. The program will continue to execute printf after calling full. The stack overflow vulnerability occurs when an overwrite happens, especially if the value that is overwritten is the saved RIP. Then when a function returns, and when the saved RIP is extracted from the stack and moved to RIP, the program will execute on an arbitrary address that can be controlled by user's input. Now let's take a look at an example. Here, function main calls function check, and in the main function, it takes ID from standard input, and then it calls check with argument ID. At the line of string f, it copies the value of ID to path along with the prefix, which is the directory of records. And later on, it checks the path, and if the path is validated, then it will call cat to read the content from the path. There is some stack overflow vulnerability in function check. String path and integer res as local variables will be stored in the stack of function check. When path is assigned with value of the string of record / followed by ID, if the ID is longer than the original length of path, then path can be overflowed to the saved RIP address. An evil user can just pass in a malicious ID string so that it is long enough to overwrite the saved RIP. And if a malicious user can control the saved RIP, which is the return address, the attacker can let the program execute whatever he wants. Here I have a question for you. Suppose that you are a security analyst and you want to prove the existence of a buffer overflow, especially stack overflow vulnerability. So the question for you is that how are we going to generate an input that will overwrite the saved RIP to a specific string, such as hex.beef.beef? We can split the task into the following steps. The first is that we need to check the address of path so that we know where is the start that we can copy paste to. And then the second is to check the address of the saved RIP, which is the destination, or say the target address that we want to overwrite. Then we can take advantage of sprintf, this specific statement, manipulating ID so that we can copy paste the string longer than 50, and it will extend from the start of path and to the end of the saved return address. So we need to calculate the address of the start of path as well as the address of the saved RIP. And the length between this is going to be associated to the length that we need to put for ID. To get the actual length, we're going to use GDB to run this program. So I'm going to show you the source code on the left, and then I'm going to run the program of stack. And let's set a breakpoint at function check. Now the program stops at function check. And let's check the address of path. So argument path start as this particular address, which is in stack. And then let's check the address of the saved return address. There are two ways that we can do it. One is to use info frame, which shows the saved register's location. And another way is to check the stack directly. We can do stack followed by some certain amount of stack items. And here we see that the return address is saved at RBP plus 8, which is this particular address. And this is equal to what is shown over here when we run info frame. So now we know that the address of path is at the stack in the offset of DC60, and the saved return address is at the stack in the offset of DCA8. Now let's do a very simple subtraction. The length between path and the saved address is equal to 72. And remember that when we do sprintf, there is a prefix of the string, which is recorded as slash. And let's count the number of characters for this prefix. 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 bytes ahead of ID. Therefore, we need to do 72 minus 8, which is 64 bytes. So that means that if we start from path, and if we put the input longer than 64, it will start to overwrite the saved return address. Now let's try it. I'm going to quit this, and then I'm going to use Python to write a command that output 64 bytes, and then I'm going to just put a bunch of B over there, which shows that what we add over here is different from what we added as the padding of the string. So let's put 8 bytes of B over here because the address should be 8 bytes. Okay, so there are 8 bytes. And then I'm going to save it in the input file. And let's run GDB again. And then let's set a breakpoint right after sprintf. And now we're going to run this program, and this program is going to read the file of input as standard input. Okay, so now let's check the frame. We'll be able to see that the saved RIP now is equal to hex 6262 many 62 8 62s, which is the byte, the character of B. And let's take a look at the stack. We could do x some value, say 10 items, and we're going to show them in Word, which is 4 bytes for each item. And for each item, we're going to show it in a format of hex. We probably need to have more items. Then let's just print 20 items from over there, starting from RSP. Okay, so let's print something more. Actually, let's change it from Word to G, means that 8 bytes together. All right, now we'll be able to see that starting from RSP, the stack value is as follows. So again, the address of path is DC60. So it starts from over here, DC60. And then the first couple bytes is record. And starting from DC68, the characters are A and to address DC88. And DC88 is the start of the saved return address. Now the next is that how we're going to turn this address from B, a bunch of B's, to hex.beef.beef. So first, let's check the endianness of this executable file. We can do it by file, followed by the name of the binary as an argument. So here is that this is LSB, means that this is least significant byte shared object. So this binary is in little endianness. If it's little endianness, then we need to be careful that here, the first byte that shows over here, which is hex 62, is actually the highest byte, starting from DCA7 to DCAF. So the first hex 62 is actually at the position of DCAF. And we want this one to be hex DE. And let me put the bytes over here, that beef and that beef, right? So the first one is actually the highest address. And then the second byte, AD, is gonna be the second highest address. So this means that if we wanna put this in our input, we have to make this byte, that beef, and that beef in a reverse order. Let's still write this in Python because those bytes are not printable. So here, remember what I just said, the first one, which is the highest byte. So it's gonna be DE. And then the next highest, which we should put it in the left, is gonna be AD. And then the third is BE. The fourth is EF. And then let's repeat this again. Okay, now let's run this. And again, I'm gonna put the breakpoint right after sprintf. And I'm gonna run it. Oh, actually, I need to run it with the input file as the std input. Okay, now let's take a look at the frame. We see that the saved RIP turns to that beef. So now we can construct the input manually. Can we actually having this part of the byte automatically without thinking about endianness? If you have watched the endianness video that I posted a couple of weeks ago, you may remember that Python has a nice package called struct, which can automatically output the bytes in different endiannesses. So let's use that and then import struct and do struct.pack with the format. And here, smaller than means this is little endianness, and Q means it is a unsigned long integer. And then followed by we will be able to get the correct string. So in this case, we can just put this string together with the print statement over here, and then we'll be able to generate the input. We can still write it in one line of Python. A more clear way is to write a script. So let's do import struct, and then we can do print a times 64 time, and then struct dot pack, and then we can even make address as an argument so that in the future, if we want to change the address value, we can just change the value over here instead of changing the print statement. So if we can output to input, and if we check the byte of this particular input, we'll be able to see that in the end, that the bytes are exactly what we want. All right, now we are be able to overwrite the saved return address with any value that we want. So the question is, how can we take advantage of this and let the program execute what we intended to do? In the next week, we will talk about how to take advantage of a vulnerability such as Stack Overflow.